at a problem of a car moving along a curve. So entering in what we've identified as uniform circular motion. And the question is asking, what is the maximum speed that a car can go in this circle if the curve has a radius of 50 meters and the coefficient of friction between the tires and the asphalt is 0.9. So I'm giving you a mass of a car. We're going to find out if that's even needed in a minute. So here is a picture. We're going to do a left-hand turn. So the car is coming in like this, and it's going to turn to the left. And if we do sort of a top-down view, there's my car, and it's going into the board and then turning to the left. So with any force analysis, we, of course, identify the object. And our object in this case, we're interested in analyzing the circular motion of the car. So what are the interactions happening on that car? Well, we know we have the force of gravity, and that interaction is between the car and the earth. And of course the car is sitting on the road, so there's that compression force, that contact force between the car and the road. Now, if the sidewalk was full, or the street was full of ice, the car would not be able to make that turn very well, or pebbles or sand or gravel. So there must also be a frictional force involved, and we know friction is involved because it gives us the coefficient, and that's happening between the car and the road. So now let's use these forces to look at our free body diagram and see what direction those forces are acting to see if we can analyze this circular motion. So we'll draw a free body diagram of the car. So there's our car. Now the force of gravity we know acts downward. That's the force of gravity. It's equal to mg. And the road, sitting on the road, here's our kind of tail end view, that's acting up. So there's our normal force. And now what about that frictional force? Well, the tires are being prevented from sort of slipping outward on that curve. And so our frictional force must be in the inward direction. So here's our free body diagram. All right, let's continue the analysis. We'll number each of our forces. And as we typically do, look at them in the horizontal and vertical components. So force number 1, well, that's our force of gravity. It's not moving horizontally, and it has a downward mg. So the force of gravity is in the downward direction. The second force, our normal force, well, that doesn't have a horizontal component, and it's positive. It's moving in the upward vertical direction. And our third force, our frictional force, well, that's pointing to the left, and we know that that's mu n, and it's not pointing in the upward direction. Now, why didn't I rotate the axes? Well, we can see that our forces are all along the horizontal and vertical plane. But as a reminder, we also want to look at the direction of that acceleration. This car is moving in a horizontal circle, a horizontal plane. And therefore, the acceleration, if it's a left-hand turn, is going to be in the leftward direction. That's going to be important. That acceleration is in the leftward direction. It's along the horizontal meridian. Therefore, I don't need to rotate my axes. Remember, we only rotate the axes to align with the acceleration if needed. All right, so what's the next step? Well, now we apply Newton's second law. Remember, Newton's second law tells us that the sum of the forces horizontal equal the mass times the horizontal acceleration. And the sum of the forces vertically equals the mass times the vertical acceleration. Well, the object's moving in a circle, and it's moving in that circle horizontally, so our horizontal acceleration is our centripetal acceleration. And in the vertical direction, we're not changing our motion. So the sum of our vertical forces, N minus mg, are going to equal 0. the sum of our horizontal forces minus mu n plus 0 are going to equal the mass times our centripetal acceleration. Now, remember, the magnitude of our centripetal acceleration is was our speed squared over the radius, and the direction is towards the center. So what does that look like in our problem? Well, we'll keep our forces down here. We have the mass. Our magnitude of the centripetal acceleration is v squared over r, and our direction is towards the center. We have to be explicit. As soon as I put in this magnitude only, I have to be explicit about my direction. Well, as it's moving around to the left, I see that that direction is negative. All right, so we are interested in determining the speed squared, so we can then get the speed. That was the question. We also know that our normal force is equal to mg, so we're going to put that in for our normal force. I'm just going to shift this whole relationship over here. We have minus mu times mg equals m minus the speed squared over the radius. Doing a little bit of algebra, my masses cancel out, my negatives cancel out. I end up with mu times g is equal to v squared over r. Mu times g times r is equal to v squared. Take the square root of that, and I get 0.9 times 9.8 times 50 equals my speed. So what is, and I do not have my calculator, what is my speed? So we have 0.9 times 9.8 times 50, take the square root, and we get a speed of 21 meters per second. The mass didn't even matter, it cancels out. All right, so with uniform circular motion, we want to identify the circle and what object is being moved in that circle. Just like our force analysis, we identify the forces, identify the free body diagram, the interactions, and then the directions of those interactions. Thinking about the direction of that acceleration to see if we need to change our coordinate system. If it's within our normal coordinate system, we don't rotate. Identify those forces in their individual directions. Then we can identify which of the two directions the circular motion is happening on, that circular centripetal acceleration is happening. Sum our forces just like we do with Newton's second law. The sum of those forces then is going to give us that centripetal acceleration, identifying not only its amount, but its direction, and then solving for what we're interested in. All right, good job.